Hello, it's David. Something slightly different today. I thought I'd have a go at building an ASCI to STM hard disk adapter for the ST and STE, specifically to power my STE here. So it's meant to be quite a simple little project, so I thought I'd have a bit of a go and see how we get on. So the hardware I've got ordered in, breadboard just for the initial connections. When it's all working, I can think about doing something a bit more permanent. A few wires, and the things that are listed on the website, which I shall link in below, are the blue pill STM32 development board. This is only a few pounds. Ordered this off eBay. Hopefully this will do the job. A USB to serial dongle for the purposes of programming, said blue pill, and this is one that supplies 3.3 volts from the USB. That's just one that I had laying around, but again only a couple of pounds. SD card adapter. So these basically seem to all be the same, just slightly different form factors. They are, looking at it, they're SPI. They've got a clock, the master out, slave in, master in, slave out, chip select, VCC and ground. So one of those. A male DB19 port. Well, this is the problem here. You see, a DB19 port is almost impossible to get hold of. They are very unusual. It's the same connector that is used on old 68,000 Macs, and it's reverse. The male version is used on full. That's even rarer still for the video out. So the trick is to get a much more standard DB25 and cut it down. So we'll be editing this with the Junior Hacksaw. I'm hoping we don't lose any fingers. So there's some pinheaders here as well. But firstly, let's think about getting this into the appropriate form factor. Now this is a solder-on type, so it doesn't have a removable shield, so the whole shield's going to have to go beyond the point that we want, and we've got to get 25 pins down to 19. Now obviously we could take off one side, or we could take off the other side. So the best way to decide how to do that is to look at the back of our ST. So here's the back of the STE, and this is the DMA hard disk or ASCI port, as it's known. Here's our DB25. You see the DB25 fits straight into the printer port. That's what it was designed for. But the hard disk port is the same configuration, just less wide. So we've got two options. We can either go this end or this end. Now, if you've seen my previous videos, you'll know that I'm using my floppy disk socket at the moment because I bought an external drive, and that's down here, and that's in use. But I'm not using my printer port, so it makes sense to me that I should choose this way around, so that if there's any interference at this side, that's more acceptable to me than any interference with the port on this side. So we'll be trimming, if we look at it this way up, we'll be trimming the right hand side. So we need to convert this down to 19 pins. So that's going to be 9 along the bottom and 10 along the top. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it's going to be in that diagonal there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm just going to make an indentation here, if I can, to mark my cutting point. Not very visible actually. This is considerably slower progress than I was hoping for. We may have to step up to the full-size hacksaw. Okay, I'm going to be honest with you, that did not go according to plan. So I got the big hacksaw out, and immediately this started collapsing. Cut away the end piece, and these two just peeled apart. So when they peeled apart, this fell out. Unfortunately, you can see I've actually damaged one of the pins that I need to keep. So I might have a go with the pliers and see whether I can straighten that up. This is just, you know, a breadboard version at the moment. But this was not the triviality I was expecting it to be. Right, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and unfortunately I need that one. I think that's the interrupt pin. So I don't know how badly I've damaged this. If this breaks off, I suspect that's curtains. I do have another one, but I will need to come up with a better way of doing it. Oh, it's rotating. Oh, doesn't feel great. Feels a bit jelly-like. Oh, oh dear. Am I happy to shove that into the back of my 30-month-year-old computer? Uh-oh, and look, this is parting now. What happens if that comes apart? Might just super glue that. He's going to come out. Nope. Get them out just to save a bit of space. You know what? I think that's going to be okay for just a test version. Let's see if it fits in the back of the machine. Okay, so here we are looking at the back of the ST again. Am I going to be able to pull this back out if it goes in? So it fits okay. And it pulls out okay. And it's kind of, sort of, still holding together. Not too bad. Let's give it a try. Okay, so moving on to the soldering. I believe I need to connect 15 of these 19. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 here. So we're going to need to make some more cables up. But to start with, let's get my data lines soldered into place. Right, so working from the top corner here, this corner, this is pin 1. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and then it carries on along the bottom 11, 12, 13, 14, 15, 16, 17, 18, 19. So I'm going to start with pin 1, which is data 0, the least significant bit. So I'm going to do the 8-bit data bus in red, I think. 1, 2, 3, 5, 6, 7, 8. And for this, I've got my chisel tip in on the soldering iron, which I prefer for macro, full through-hole style work. Oops. Okay, there we go. Post cleanup. It's all a bit wet still from the IPA, but that should be hopefully now okay to work with. It's not going to make my fingers all sticky. That's still parting. I think I'd want a better permanent solution, but I'm happy to go with this for now. Okay, so turning our attention to the blue pill here. I'm not 100% sure how many of these ports are being connected, but I think the majority of port B and a good chunk of port A, and then we've got power as well. So it comes with these headers. For the purposes of breadboarding, I think I'm going to solder them up. I can always remove them again later on if I go for a more permanent option. But there's probably nothing wrong with having headers on here. I could even just put a socket in, couldn't I? And that one's one too long. Just try and pinch that final one off. There we go. So let's get that in there nice and square and tack down the ends. So blob there, blob there. The trick here is to not hold the pins underneath that you're about to solder, because you'll burn your fingers. Yep, that's square. Okay. Okay, so do they line up with our board? I'm going to push it all the way in because it might not come out again, but yeah, that lines up. So now I'm happy to scoot along here and solder the rest of the pins. I'm afraid I had to admit defeat. My stringy out breadboard experiment didn't work. I could get it to read the SD card, although not properly, more on that anon. but I couldn't get it to talk to the ST. I think a combination of probably my piss poor soldering work here and a fairly ordinary breadboard, and trying to debug where all these wires go. Forget it. Time to move on to plan B. Protoboard. So what I've done here is actually taken my second one and had another go at this, and what I discovered, this is still not absolutely beautiful by any stretch of the imagination, but certainly better than this monstrosity I concocted here. What I discovered was getting the little snips, the side cutters, getting these on it, so cutting down into the socket like that, and then working around and cutting them off. Far more reliable, although not pretty. As I say, this is really a prototype. Jammed it onto the edge of a bit of protoboard, anchored it in a couple of spots where the holes almost align. You see, just like that. I don't know if you can quite see that. That's just a lot of excess solder on there, so it holds onto the board, and similarly on this side, just a whole bunch of excess solder so that it doesn't fall off. And then some female socket headers. So the female socket headers go for the blue pill board. I've got it aligned so that pin B12 is in this corner over here. So it sits in here like this, and then from there I'm able to work out where each of these pins should go, and they just a little Kynar wire here, cut to approximate length, soldered on to each of the pins, taken down through the holes where appropriate, and then a bit of a spaghetti mess at the bottom as I attach them all up. So that probably took about an hour to get all of those done. The SD card reader at the top here goes in this way round, so card facing forwards, and this lines up a little bit better. We've got the I think the order is chip select. Yep, so we've got chip select up here, which is just done with a straight jumper wire. We've got the clock next to it, which again the same thing, can just be a straight jumper wire. We've then got Mossy and Miso, and these are crossovers here, so one insulated going that way, one uninsulated going across it. Then we've just got 5 volts, which we've tapped from the corner over here, and then continued down to a pin header to be able to deliver 5 volts, and ground, which in this case snakes over to this corner one, which is one of these grounds up here. One of these grounds up here. The 5 volts being in the opposite corner, and we've also got another pin header here for the ground, and they line up with these down in the corner here, which are 3.3 ground and 5 volts. So we're basically powering it through the 5 volt pin and the ground rail there. So that's all there is to it. So this assembles like so. The SD card chip just plugs in. The SD card module just plugs in here, and that obviously has to be, we discovered, needs to be powered by 5 volts. That's a LM 1117 3.3 volt regulator. So we need to be putting 5 volts in here. Can't put the 3.3. And all I've done is I've just tacked a couple of extra pin headers on here, which are the transmit receive lines for the purposes of our debugging. So we go back to our debugging serial dongle here, and you can see just about reading through the case here that this supplies 3.3 ground, transmit receive, another ground, and 5. So we can power it from this little dongle while we're testing it. We just need to wire this up here and program it up. Now to program it, what you do is you need to set, so there's boot 0 and boot, can't really see it in there, boot 1 that says. So we need to set boot 0 to the 1 position instead of the 0 position. So I've just got a long handled jumper on there to allow me to do that quickly and easily. And when it powers up, it'll be in the programming mode, and we set it back to the 0 position for normal deployment mode. So, as I say, you can recognise the SD card when I programmed it up first time with the firmware off the GitHub repository, but it read 0 blocks. Now I was doing a bit of searching around. I found on the Atari forum someone else had a similar problem, and they changed one line on the in the firmware to set the oscillator frequency for reading, so the SPI frequency for reading the SD card to 8 MHz. That solved their problem. I tried that, and it works fine. So let me take you through the programming, and then we'll explain how I got it to work with the STE. So here we are on the laptop. I've gone through the process of installing the required Arduino software and libraries as per the ACSI2STM website. And key thing that I've found, there's a one of the libraries, I forget which one off the top of my head. I think it's the SD card library. Is the current version is not compatible with the software at the moment, so you need to ask for a specific previous version. So the SDFAT library here by Bill Greiman, the current version is 2.12. 2.07 is the last version that works, so I've got a slightly older version installed here. But then by pressing verify on here, I can see that my code compiles, but I was having problems getting it to recognize my SD card, and this is the line that needs to be changed. So there needs to be an extra parameter on this called SD SPI config, and that last parameter just gets added on the end here, so comma SD underscore SCK underscore MHZ parenthesis 8 close parenthesis. That's all. That will compile fine. Just slows down the SPI clock, and I've not had any problems since then. I'm not trying to go for the fastest possible solution here. I've not played with all of the settings in the header file here, although I have turned on the debug, which I know will slow things down, but again, not going for the highest speed. This is a bit of a prototype, so just to see if this works. So I've got the ASCI debug turned on, which allows me to read through the serial port what's going on. And so then what we do is we connect up our serial dongle, and we've got our 5 volts and ground connected onto our header for 5 volt and ground, and we've got our transmit and receive hooked up to A9, A10. And now when I hold this up here, try and get them both in shot. So when I now go up to program to upload, there we go. We can see a percentage going up here. Actually, there's no activity on the blue pill, but you can see there's a bit of flashing on the USB. That's it, done, and it says it's starting execution at the appropriate address. So what I'm going to do is I'm just going to set that jumper back to the 0 position. Now we've got a green light now. And if I open the serial monitor, set it for 115200 baud, and press the reset button. We've got our debug output. So ASCI2STM SD Bridge version 2.1, SD0. SD0 is a 15 gigabyte card and it's set for boot. So what I've done actually to just prove this works is downloaded an ASCI bootable ASCI image from the Atari Forum website, which contains the ICD Pro driver, which is release free these days. So basically a known working configuration in case I had to debug it. This is not my end goal, but I just wanted to make sure I had something that I thought stood a very good chance of working. So let's switch over to the ST and have a look at it in action. Okay, so I've got the SCE turned around backwards so we can see what's going on. Monitor connection is in, just off screen, although I can move you up to have a look. We've got our monitor hooked up and nothing plugged in at the moment, but we'll power it on just to prove that we've got a working configuration. There we go, there's the Atari logo, and the memory test should pop up in a second or two. There she is. Okay. Okay, so our ACSI2STM is still hooked up to the laptop. Its power light and activity light are on. And we're going to slot it in here to the DMA port. And as you can see, it's it could go in this way. That would make things messy. Hopefully it would be blocked by the nut. But since we want access to the floppy port, we moved it across in this direction. So it should just connect on the edge of the port. It's quite a good solid contact. It's actually nice and sturdy. It's not too bad for a flimsy prototype. Okay, so hopefully you can see a little bit of the screen, and the activity lights will be here, and the transmit receive lights will be here, and I've got my terminal open off screen here to monitor progress. So I'm going to press the reset button. On my terminal it says one SD card for 115 gigabytes, and it's marked as bootable, so it's recognized that there's a partition on that, which is good. And I'm going to throw the switch and watch these lights. Straight away I can see on my terminal it's come up as ready to go. We can see the Atari logo is here. Floppy drive seeking. No sign of activity yet. The RAM test has come up. So I'm going to cancel that. And there, green flashing lights. Transmit receive flowing as the data comes on. And there we go, we've got the ICD logo appeared on the screen. And perfect, look at that. There we have, I think this is PP's games image with the ICD drivers built in. So there we go, we've got ourselves a working SD card hard disk. Now, I've been told that the normal failure mode with these is that you can't save, or writing fails. So I believe a lot of these games come with the ability to write an image. I can't follow. We can try that. So if this has the ability to write an image to the disk, a memory snapshot, here we go, yeah, save game state / on the numpad. So we can test this by pressing / and we'll see if it produces a workable output file on the disk. Right, oh, mission complete. Right, so I'm going to try saving that now by pressing the didn't realise I only had to kill 3 people. I'll let this one start and we'll try saving it. Okay, so we're by the river. So I'm pressing the / button on the keypad. The screen goes grey, tells me it's saving version 00, and it pops back. That's it. So that was half a megabyte saved in what, about 4 seconds. And I'm going to press the asterisk key to exit. And there we go, gs00.tos. And that is our save state, 525 kilobytes. So let's try running that. And we should go back to our position on the river. There we go, look at that. So it does save STE, bad DMA, all of that rubbish. Which has nothing to do with DMA, by the way. It's all about pull-up resistance. Anyway, I'm going to put that down as a success. Okay, now obviously I'm going to go straight to Frontier for a test. So I've got my Frontier floppy here, and I'm going to copy the main program over to drive C. And we should be able to run this from drive C happily enough. There we go, that was nice and quick. Half a megabyte loaded up in no time. And let's have a quick look at the current draw. What I've done here is I have inserted a USB tester in between my my laptop and the USB serial dongle to measure what sort of current draw we've got, because unfortunately there's no power source on the Atari ACSI port. So I need to have a bit of a think about where we can borrow 5 volts from, or 12 volts and a converter. Could even think about fitting a battery to it if I spin a board properly. We'll have to have a look at the volumes. So here we go. We've got a figure of, I'm supplying 5.1817 volts from my MacBook, and it's 0.06 amps, so that's 60 milliamps. So that's not drawing a lot of power at all. Maybe we'll let it go through a boot cycle and monitor it. So I'm going to press reset now. Frontier's still running, but let's reset that. We can see activity happening. So that's the ICD drivers loading. That's it booting up, and no change from 60 milliamps. What about if I try and copy one file to another? So if I copy that 500 megabyte file of Frontier to the same partition. So I'm going to copy that from drive C to drive C. Give it a different name. Copying now. 0.09, so it's gone up to 90 milliamps. Okay, so we're looking at a peak of around 100 milliamps. What could we do to give it a more sustained test, perhaps? Is there a bad sector scan or something like that? Map out bad sector. So there's some ICD tools on here that I'm going to try out. So okay, that's running a sector scan now. We can see it. Okay, it's going up to 90 milliamps again. So that's the ICD software doing a bad sector scan. And yeah, we're kind of seeing a 90 milliamp peak there. So we're potentially in the realms of something rechargeable. We're probably talking about in the region of a couple of rechargeable AAs. We've got to get 5 volts. So 3 rechargeable AAs, for example, would do a very good job, although the size would probably be a bit large. So to be honest, a fly wire, a USB supply, or maybe I'll just put provide a port on the back of the STE. This one is actually pristine condition, so that would be a pity. But I suppose I could always run. I've got a GoTech in place, so I could always run a wire out of the GoTech, or even provide a port on the GoTech. But there we go, brilliant for a very set of inexpensive. From a very set of inexpensive beginnings, we've got ourselves a working hard disk on the STE, and I'm very pleased with that indeed.